In physical engineering, pressure builds invisibly. A misaligned assumption early in the design phase accumulates structural stress until the entire project suffers a catastrophic failure. In embedded systems and high-tech electronics, the cost of a misunderstood requirement grows exponentially. A single missed integration target, a failed certification, or a hardware respin late in the development cycle can consume months of engineering time and cost several times more than the entire initial requirements phase. The root of this pressure almost always starts with the Customer Requirements Specification, or CRS. While these documents capture the initial vision, they routinely suffer from a structural flaw. They mix what the product must do with how the customer assumes it should be built. A customer might submit a requirement stating the device must use a specific STM32 microcontroller to connect to a local network. Here, the actual functional need, wireless connectivity, is buried under a premature technical mandate. Attempting to estimate a budget or build an architecture directly from this mixed document artificially restricts design freedom. It forces engineers down a specific technical path before they can evaluate if that path makes sense, and it obscures critical edge cases and fault conditions that haven't been properly mapped. To prevent this compounding risk, we process the initial concept through a strict two-phase translation methodology. We deliberately separate the product requirements analysis from the system requirements analysis. The boundary between these phases is absolute. Phase 1 is strictly dedicated to defining what the product must do from the user's perspective. Phase 2 takes that behavioral model and determines exactly how it will be engineered. By isolating the behavioral intent from the technical implementation, we create a clear, verifiable target. This isolation provides the required foundation to generate an embedded architecture that can actually be quoted, planned, and reliably built. The mechanism that governs Phase 1 is a non-negotiable rule called solution neutrality. The Product Requirements Specification, or PRS, must define the system's behavior without ever prescribing internal implementation details. The practical test for this neutrality is straightforward. If an end user or external system can see, interact with, or directly rely on a specific technology choice, it belongs in the document. If a technical choice is purely internal and invisible to the user, it is aggressively removed. Consider a draft requirement to read temperature data via an SPI bus. That internal engineering detail is scrubbed, restructuring the text to state the pure functional intent. The system shall read ambient temperature. However, if a draft mandates a firmware state machine to drive a capacitive touchscreen, the internal software logic is erased, but the physical hardware constraint survives the filter. Once this filtering process strips away the technical jargon, you're left with pure functional intents. But a list of intents is not a specification. These isolated behaviors must be systematically structured to ensure no edge cases are missed. We model this behavior using 3 abstract components. We define the actors, the users or external devices interacting with the product. We map the interfaces where those interactions occur, and we identify the artifacts, the specific data objects or physical items crossing the system boundary. Forcing the product definition into this solution-neutral behavioral model prevents premature technical lock-in. It keeps the design space open so engineers can explore the most efficient, rigorous paths to achieve the required outcomes. With the actors and interfaces mapped, we author use case scenarios. These are step-by-step narratives that link specific external triggers, like a user pressing a button, to exact system responses, entirely avoiding internal code descriptions. Writing the ideal success path is expected. The actual engineering value comes from mapping the alternative flows and failure conditions. We document exactly how the system must behave when credentials fail, when power drops, or when concurrent inputs collide. These narrative scenarios are then mined for explicit responsibilities. Every single time the text describes the system performing an action, evaluating a decision, or changing its operational state, that moment is extracted. Each extracted moment is reformatted into a rigid structural rule. They must be written as atomic, declarative statements anchored by the word shall. A draft note saying the system should connect quickly cannot be tested. Extracted properly, it becomes a verifiable requirement. When the Start button is pressed, the system shall establish a wireless connection within 2 seconds. Behaviors that aren't tied to a specific scenario, like electromagnetic compliance or thermal operating limits, are captured as non-functional requirements. Because these bypass the scenario generation process, every single constraint here requires an explicitly documented rationale to justify its inclusion. Finally, every extracted functional and non-functional requirement is paired with clear, objective acceptance criteria. We define exactly how the team will test, measure, or inspect the final device to prove compliance. This rigorous extraction process ensures no required system behavior is left to implicit guesswork. The output is a highly structured, testable baseline, a precise contract defining exactly what the product must do. With the behavioral contract locked, we cross the absolute boundary into Phase 2, System Requirements Analysis. This is where we answer how the product will be engineered. We begin functional decomposition. We take the long list of abstract shall statements and cluster related responsibilities together into discrete logical groups. These bounded groups become our functional modules. We assign them specific titles, mapping the internal organization. Next, we map interactions by tracing the directional flow of data and control signals from one block to another. Cross-cutting features, like power distribution, would normally turn a diagram into an unreadable web. These are systematically simplified into a clean notation, preserving the genuinely significant connections. It is important to note that this interconnected web of modules is entirely logical. We have mapped the internal structure of the system, but it remains independent of specific physical hardware choices at this exact stage. Breaking the system down in this manner isolates complexity. It creates a natural work breakdown structure, allowing specialized engineering disciplines to take clear ownership of specific modules for parallel development. Functional decomposition serves as the technical bridge. It translates purely behavioral needs into an organized system vision, preparing the product for physical assignment. Looking at this logical architecture, it becomes clear that not every functional module carries the same technical or financial risk. To evaluate the implementation approaches for each individual module, we conduct a concept analysis. We review the available technology to determine how each block will actually be built. During this analysis, we sort the technical uncertainty of every module into 3 distinct classifications. Some modules have obvious, established solutions requiring minimal effort, landing in the trivial category. Other modules present multiple viable paths, perhaps trading component cost against power efficiency. These are balanced and require formal trade-off studies. Finally, functions relying on unproven methods fall into the exploratory category. These carry high risk and mandate targeted proof-of-concept prototyping. By classifying the system this way, we prevent wasted engineering cycles. Teams can surgically deploy their prototyping budgets exactly where feasibility is unproven, protecting the schedule from hidden technical debt. With implementation concepts selected and validated, we execute the transition to a physical device architecture. A single logical block rarely maps to just one physical part. Its responsibilities are formally divided and assigned across the hardware, embedded software, and mechanical domains. For example, a control unit module might be split into 3 physical layers: C code on a microcontroller, parallel logic inside an FPGA, and copper traces on a circuit board. Before finalization, we subject this architecture to a mandatory stress test, the DFMEA. We evaluate how every new physical interface might fail. The discovered mitigations, like a redundant sensor, are routed directly back as hardened, verifiable rules inside the System Requirements Specification. Performing this rigorous failure analysis at the device architecture stage ensures that structural weaknesses are engineered out before detailed design begins. It guarantees catastrophic physical failures are not built into the product. This is the complete translation pipeline. We take a mixed customer specification, process it into a solution-neutral behavioral model, decompose those functions, and map them to a hardened physical architecture. This final device architecture provides a high level of technical clarity. We can now assign physical, commercial components to the design, immediately generating a preliminary bill of materials to assess true unit costs. Simultaneously, the meticulously verified system requirements allow us to draft the initial product test plan, defining the specific lab equipment and certification strategies needed for compliance. Because the scope, the physical components, and the test strategies are fully defined, the resulting project schedules and engineering budgets are no longer top-down estimates. They are fact-based, defensible projections rooted in actual engineering evidence. This level of precision removes the friction from product development. Enforcing a strict boundary between behavioral intent and technical execution turns fragile concepts into buildable products. It eliminates late-stage surprises, addressing technical realities precisely when they are least expensive to solve.